Hi, I'm Rob Hayes, CEO of Atom Computing. We're a company on a mission to deliver the world's most scalable and reliable quantum computers. Prior to joining Atom Computing about a year ago, I was the Chief Strategy Officer at Lenovo. Before that, I was at Intel Corporation for about 20 years. The last 7 of those, I was driving the Xeon processor roadmap. So I've had a career of driving compute performance to ever-increasing levels. And in the last few years, I've really been watching quantum computing and seeing that as really the next big wave of breakthrough performance. And that's why I joined Atom Computing. I want to tell you a little bit about the company, and then I'll tell you how we think you could use quantum computers and what you can do to prepare. So Atom Computing, we're a hardware company building quantum computers, founded in 2018 by Ben Bloom and Jonathan King. We're based in Berkeley, California, and we've built our first generation systems there. We're kind of known for being the fastest to deliver 100 qubit system. And we built that with world record coherence times, which is really good for the quality and stability of the system. Quantum computing is something that's a major paradigm shift in computing performance that's really going to touch all industries and many, many applications within those industries. BCG estimates that that market could be up to $850 billion worth of economic value generated by quantum computing applications within the next 30 years. And one thing that we've noticed over the last few years is that when we were founded, the investment that was being made by CIOs in quantum computing was relatively nil. Gartner reported it at 1% in that time frame. But as I'm out talking to customers and CIOs, we're starting to see a lot more interest in building up small teams to basically go do some testing and research around quantum computing and how they can use them. So they're often putting together small research teams or developer teams that are able to go out and kind of test the systems they have, test some algorithms, and just really learn how to program them and get some feedback that they can use for the future. So then the question would be, well, why now? Why is there rising interest? And I think that it really comes down to a few things. Number one, the technical progress that's been made by companies like ours in building quantum systems, as well as the software stack, the developer kits and tools, and the cloud services that are making them available to people around the world. So it's much easier to get access to the technology today. In addition to that, there's timeline clarity, which basically means that most of the companies that are investing in quantum computers today, they're publishing roadmaps that say when the technology is going to be out, how it's going to evolve in size and capability over time. And that really helps customers understand what to expect as we move forward and start to plan their own activities around that, which is quite helpful. Additionally, there's a number of use cases that have been published by different companies and research groups around different ways that people can use these quantum computers to get what's called quantum advantage, which is eventually when quantum computers can outperform classical computers or do things that just aren't possible on today's systems. Now, as a hardware computing company, our mission is crystal clear. We're delivering large-scale computation as measured by the number of qubits with error correction. Now, we owe a lot of the foundational efforts to some of the pioneers in the industry. Superconductors and trapped ions are 2 of the original technologies in quantum computing that have really gotten us to where we are today with the systems that are available. Large companies like Google and IBM have made tremendous, investments over the last decade in building up these technologies. And they've really done a lot more than just building the hardware. We've got now software developer kits, software stacks, so that we can program these systems, and cloud services that are built around them so that people can access them. And that's a really important foundation that's been laid for us. And moving forward, what's really important is we need to be able to scale these systems to much larger qubit counts and eventually get to fault tolerance so that you always get the correct answer and you're not prone to errors or noise. And that's kind of where some of the challenges moving forward lie. In these 2 particular technologies, it's kind of challenging to scale up because they have to manufacture chips and then cable these chips together to make larger systems. They have to immerse those chips and cables into very large cryogenic dilution refrigerators to get them very cold and stable. And then they need to tune these things up so that the timing and everything is really kind of very precise so they operate as one coherent system, which is quite a challenge. To get to thousands or even millions of qubits, these kinds of systems are going to get very large and need lots of technology development that will be quite a challenge. It's very doable, but it's going to take a lot of engineering effort, a lot of time, and a lot of money to make that happen. We believe there's a better way, and that's what we're pursuing at Atom Computing. Enter neutral atoms. Neutral atoms are are an approach where we capture atoms in a vacuum chamber with spots of light, and we scale them up by simply creating more spots of light to individually control the atoms. Now, we've developed what was the world's first nuclear spin qubits that sit within the atoms, and I'd like to tell you a little bit more about what that is before we talk about how we use them. So first of all, neutral atoms are simply defined as atoms or elements that have an equal number of electrons and protons. And we use alkaline earth metals, specifically strontium, for naturally stable qubits. And what we do with the strontium is we basically take a vacuum chamber, which has absolutely nothing in it by definition, and we insert a cloud of strontium atoms into it in a gaseous form. So these atoms are just moving around inside the vacuum chamber, waiting for some magic to happen. And it turns out that every element has a magic wavelength of light that allows atoms to get basically captured in what's called optical tweezers by sending that right magic wavelength of light down into the vacuum chamber. And as the atom crosses through it, it simply gets stuck. Some people call this cold atoms, and it's cold because it's not moving, and that's, synonymous. So once we capture these atoms, we're able to create qubits that we can control with inside of them. So if I zoom in and I look at, before I go there, we actually don't capture just one of these atoms, but we capture multiple of these atoms in an array with different spots of light that we put into the vacuum chamber. And then if we zoom into one of them, you can see that at the nucleus is where the quantum information is held and controlled. And so what we can do is with a different wavelength of light, we can effectively control the spin of the nucleus in any position in 3 dimensions. And that's how we create what's called single qubit gates. Now, quantum computers are made up of what's called quantum gates, which is a set of predefined functions that need to be individually controlled to execute the algorithms. So we can control the individual qubit gates with one wavelength of light. And then what we can do is create entanglement with 2 qubit gates by using a different wavelength of light, and we can shine that light on 2 adjacent atoms. And what happens is these atoms go from what's called the ground state, where the electron clouds are quite tightly coupled to the nucleus, to what's called a Rydberg, or an excited state, where the radius of the electron orbit gets much larger, to the point where they cross paths with each other and get what's called entanglement in quantum computing. Now, once we do that, we basically can run quantum circuits by stringing together a bunch of these gates, either in parallel or in series, in order to go run those algorithms. And so what you see here is a representation of the array of atoms, where some of them, as you can see, are smaller and running single qubit gates, and some of them are larger in that Rydberg excited state, and they're able to run 2 qubit gates. And together we can actually run through the circuits. And when we get through the circuit and all of the computation is complete, we can shine a flash of light on it and take an image with an actual camera to see what the results are. Now, when they're in their computational state, remember, these qubits are holding all kinds of values of information simultaneously, but when you read them out, they're either a 1 or a 0. And the way we read them out in our system is we shine a flash of light on them, and then we take a photo of them. And if the atoms are luminescing or bright in the camera, then it's a 1. And if they're dark, then it's a 0. And that's how we do it. And then after we're done reading out one circuit, we can actually reset the system. And all of the atoms are still captured in the grid and reset to 0. Now, what I'll say is all of this happens in a very, very tiny space, less than 1 square millimeter. And as we scale up our system to millions of qubits, we will still be in a very small space in less than a cubic millimeter. So it's very hard to see our qubits, but that's actually a good thing for scaling. And so we have to use a microscope to see them. And this is actually an image from our system that kind of shows you what it looks like when you look down through the microscope and see all of the atoms being read out. Now, that's a lot of difficult technology, and that's our job to go solve those difficult problems and build these systems and scale them out. So that's not something you need to worry about. What you need to worry about is, what are you going to do with these quantum computers? So there's 4 principal computational classes that are widely expected to provide benefit with quantum computers and quantum advantage. And I want to kind of talk you through what those are and give you a few examples. So the first class is optimization problems. Optimization problems basically take in many different solution set options, and they apply different value criteria and constraints to the solution to provide the optimal combination of outputs. Simulation is the next one. Simulation is modeling the behavior of highly complex natural systems using quantum mechanical properties. Simulation is obviously something that's used highly today in HPC or high performance computing applications to model products or weather or natural systems. And with quantum systems, we're able to model much more complex systems than is really possible today with any economic, within the economic constraints. The third one is machine learning. Machine learning has gotten a lot of interest in the last 5 to 10 years and made a lot of advances in AI. I think the cloud computing or the cloud service providers probably have the most famous examples with like image recognition, natural language translation processing, and things like that. We see quantum algorithms being able to rapidly explore many solution sets where there's lots of probabilistic inputs, and the system needs to basically train a model to infer the best choice or the best output in whatever the use case is. And quantum computers can really help kind of supplement the existing kind of neural network and other capabilities that people are using today for machine learning. The fourth one is cryptography. Honestly, cryptography probably gets the most attention from quantum computing because of the threat of breaking current encryption standards, because in fact, quantum computers will be able to decrypt much faster than a current classical computer could do. But on the other hand, with a more positive tone, quantum computers can generate random numbers and calculate much more complex cryptographical algorithms much faster. And so they're going to be able to actually help us create stronger encryption standards that can protect, all of our most precious data. So I'd like to give a few examples of each of these. The first thing I would say is that each of these classes of computation cut across many different industries and verticals and lots of different applications. And so I'm giving a few examples here, but by no means would these be exhaustive. The other thing I would say is pretty much all of these use cases today are delivered in some way to some extent using classical computers, whether they're high performance clusters or just standard servers or PCs. But quantum computers are going to provide an order of magnitude speed up and gain efficiencies and capabilities and deliver economic value that just really aren't practical today. So within optimization, finance uses it to optimize portfolios and risk management and how to allocate assets most optimally. Chemistry uses it to figure out how to best deliver processes for chemical or material science manufacturing. Logistics is all about optimization. And I think one of the marquee use cases that I want to talk about today is in the car industry. So just one example, automotive OEMs, according to McKinsey, incur about $500 billion of costs in just manufacturing cars every year. That's what it costs. And as you are probably aware, there's so many options on cars and colors and materials and different choices that people make that it's not common that every car, even adjacent cars coming down the product or coming down the manufacturing line are identical. They're different, right? And so that means that the scheduling and the actual steps in the manufacturing are kind of unique. It's a unique combination for every car. And it takes time in order to schedule that out and figure out, all of those steps. And so if we could provide just a 2 to 5% efficiency gain or productivity gain in delivering these cars down the line in better throughput, then that would alone be worth $10 to $25 billion in value. So huge value can be created in just that one use case alone for the world's car manufacturers. Simulation is used again in finance, Monte Carlo simulations for looking at different uncertainties and risks and potential outcomes. In chemistry, people use it to simulate molecules and different materials to be able to manufacture different products. And then in pharma and biotech, it's used extensively in drug design and discovery, where they're simulating different molecules against different diseases and trying to see what the reaction is going to be. And today, the average R&D in a pharma company per drug is $2.4 billion. And the clinical trial success rate is less than 10%. So there's a lot of money going in, and you could argue a lot of waste coming out because of that success rate. And some of the largest pharma companies are spending, upwards of $10 billion or more every year on drug R&D. And if we could see just a 30% efficiency gain by being able to increase the success rate through better simulation up front before we get to clinical trials, then that could fall to the bottom line to be like $2.5 billion per company, which could increase profit margins by over 5%. So again, billions of dollars of value to be created just through efficiency gains and trying to have better simulation of molecules. And today, this honestly just can't be done with the systems that exist today. It would take too long. It's actually faster and more efficient just to go to clinical trial after doing some first pass simulation. But with quantum computers, we're able to do much broader set of simulation of different numbers of molecules much faster. And so it'll make more sense to do this in the digital domain than in the clinical domain. And we need much larger systems in order to go do that. And that's our job, again, is to provide those systems. In the machine learning domain, we see this a big value already today in healthcare, where we have computers that are able to take MRI and X-ray images and diagnose, cancer and other diseases by looking at the images and known patterns for what tumors and other things like that look like. There's also like synthetic data creation that can be created, where you can have computers create even more kind of fake images that can help train models much more quickly in machine learning, which is quite helpful where you've got a scarce set of data. Finance uses machine learning quite a bit. And one of the biggest use cases today is fraud prevention and detection by insurance companies or banks and other financial institutions. Today, we see about a $28 billion, I'll call it a tax on society due to people, committing fraud and basically stealing money from these institutions. And our ability to detect that much more quickly and more accurately obviously provides a tremendous value to society, because those costs get passed on to the consumers. The top 20 finance firms in the world today lose about $11 billion. So, almost half of that annually. And so, if you just do the math, every 1% gained back in fraud prevention equals over $100 million in profit margin to the bottom line. And that's a huge value. And quantum computing is able to look at a much larger number of risk factors and and do a lot more parallelism on sort of the ranges of uncertainties on those risks to help accelerate that fraud prevention. And then finally, in the cryptography domain, obviously protecting the information of our companies and our personal information and national security data is critical to society operating in a lawful way and our own confidentiality. And so this has been a big problem that's been identified, that we need to upgrade the standards, the standard TLS and SSL protocols that we use today for pretty much all of data encryption will be broken within the next 20 years, according to NIST. In fact, Google's CEO has said that it'll happen within 5 years. And I don't know if it's going to happen that fast, but it will happen. It's a matter of when, not if. And so NIST is working with the industry, the cybersecurity industry, to identify those new, stronger encryption protocols, standardize them, and then get them pushed out to the world, so all of our PCs and routers and cell phones and servers and all that can be upgraded to have these much stronger encryption protocols. So that's a really critical mission that will be enabled by quantum computing, as well as it's sort of caused by the power of the quantum computing as a necessity. So, if you take a step back and you look at all of these use cases in these 4 classes and the different industries that they touch, BCG is reporting that could be up to $650 billion. That's sort of the mean value of what they're predicting over the next 20 years for economic value. Now, that sounds like a huge number, but if you think about the economic value that's delivered today by the cloud services and the computing services that we've developed over the past 20 plus years, it doesn't seem so crazy, because computing is such an integral part of everybody's life today. So I think of this as the next wave of computing, and it's going to deliver breakthroughs that we haven't seen before, which is really exciting for me. Now, this isn't going to happen like all at one time, of course. It's going to happen over many years. And there's kind of like 3 eras of quantum computing, or 3 stair steps, if you want to think about it, that we see on the horizon. The first one is where we are today. It's called the NISQ era, noisy intermediate scale quantum computing. Relatively small scale systems. Today, not that useful commercial applications, but we're getting there very soon. Don't have error correction, certainly not fault tolerance. And so what you can do with these systems is really experimentation, early algorithm development, and there will be some early adopter use cases that I believe will provide value. BCG is basically estimating that the providers, the technology providers like Atom Computing or other hardware and software companies will probably generate, a few single digits of billions of dollars between now and 2030 in delivering this technology. And on top of that, end users and researchers will gain, high single digits, maybe up to $10 billion worth of economic value on those systems in the NISQ era. As we move beyond the NISQ era, we're going to start to get into the broad quantum advantage era. This is where we've identified specific applications and use cases that run faster, better on quantum computers than they could on classical computers. This is the real commercial value stage. And the early days of that, which are, next decade, are going to deliver, small $100 billion worth of value to the economy at large. And of that, maybe 10% of that will go towards the technology providers in the tens of billions of dollars of value. So that's when we start to see something that's really big and meaningful from an ROI perspective. And as users, you should be ready before that to be able to take advantage of those capabilities. And then finally, kind of the end state era, we'll maybe call it the heyday in the future. We're talking 20 years down the road, but this is when we have hundreds of billions of dollars for the technology ecosystem. And on top of that, up to $1 trillion worth of value that the end user economy can benefit from quantum computing when it gets to full scale fault tolerance, which is kind of where we are today with the classical computing, but the orders of magnitude better performance and capabilities here. So there's a lot of good ideas on what people can do with quantum computers, and there's a lot of value that can be generated by those ideas. But the reality is we have no idea what we're going to do with quantum computing. We do know the road is going to be long, and it's going to be curvy, and it's going to be hard to detect what's around the bend. And just like it would have been hard 20 years ago to detect the capabilities of AI and mobile computing and cloud services, it's almost impossible to predict what's going to happen 20 years from now with quantum computing. And the job for my company is to make sure that we deliver these large-scale quantum computers with error correction on a path to fault tolerance so that people like you can be ready to use those to unlock value and invent new ideas. And I thought it might be useful just to talk for a couple minutes about what should you be doing to get ready. So the first step is follow the technical developments, understand the roadmaps and the capabilities of the hardware, the software, and the cloud services that are coming out, and be ready to inform your roadmap by understanding what those developments look like. Secondly, you should understand your industry's risks for disruption and your opportunity to disrupt, because if you're not the disruptor, you're going to be the disrupted. You should find a reputable quantum computing partner or partners to help you on your journey. And consider recruiting in-house quantum computing developer talent, people that understand how to use quantum systems and develop applications on top of them, because in-house development is probably going to precede commercial, applications that are kind of provided to you. And then finally, plan for quantum computing in your roadmap. Based on all of these things, chart your course and how you'll be able to develop value for your company and your industry so that you stay in a leadership position. And this technology is hard, and it's going to be hard for us, and it's going to be harder for you. But if you need help at Atom Computing, we're here to help you. And so if you want to use quantum computing to reach your next big discovery, join us. Thank you.